Welcome to Homework Lib.
This is chapter 35, problem number 56. We have Fresnel's by prism. So if S0 is a narrow slit, show that the separation of two virtual coherent sources, S1 and S2, it's given by D equals 2A twice the distance from the sources to the screen times A and minus 1. Okay, this is the portion that we need to prove. Let me draw the diagram real quick. S1, S0, and S2. So then this entire distance is D. And then we have the prism in front of the screen, A away from it at an angle capital A. So what we need to do is basically we want to look at the distance between the slits. So then we're going to have to look at the angle at which two beams come from each source, the difference in the angle, right? And then we can go to the distance between the slits. So for that, we're going to have to apply Snell's laws several times at this interface. And then, well, pick one portion, doesn't matter at this interface. So then we're going to have an incoming beam here. Let's call it theta. And then the way that it gets refracted by the prism is we're going to have a different angle, as you know, well, closer to normal. It's kind of hard for me to draw here, but let's call that as theta I. And then it's going to hit the prism again, and there's another, we're going to have to write another Snell's law here as the angle goes back to initial. Then finally, well, we're going to call this angle theta K. And then finally, we're going to establish the relationship between, well, the outgoing angle and the initial angle. So in order to do that, Snell's law, remember, n air times sine theta equals n prism times sine of theta initial, right? So n prism, sorry, the n air is 1 sine theta, so the incoming, from the approximation incoming angle, the theta would be equal to n. Let's just call the n prism n from now on because we're going to use it a lot, and theta initial. So from here, theta initial is going to be theta over n, right? For the flat side, this is the flat side, right? But the other side of the prism, when we're looking at the relationship between, let's say, theta I and the angle at which it strikes the surface, the angled surface of the prism, then is going to be minus A because this is the angle of the prism. So let's call it theta J, for example, is going to be equal to theta I minus A. Let's plug in for theta I quickly, theta over n minus A then, right? So this, we're inside the prism now, right? Now, as we're leaving the prism, as we're looking at this interface, then, well, we have pretty much the same thing. So n times theta j from the Snell's law is, if we add a to it, then it's going to give us the angle at which the beam leaves the prism, right? So then we can plug it in for n j here. We know n j is theta over n minus a. So n times theta over n minus a plus a is going to give us theta k, for example, right? So then, again, to remind you what we're looking for, I know this is not an easy problem. So what we're looking for is the initial angle minus the final angle, theta minus theta k. So let's calculate that. Theta minus then, theta k would be n theta over n minus a plus a, right? So then theta minus, let's do this term by term, minus n theta over n minus a, and then minus a, right? Theta minus, now I'm going to redistribute this n, then theta plus a times n minus a, right? So these thetas are going to cancel each other out. We have a and minus 1 for the difference in incoming angle and the angle that leaves the prism. Now, what are we going to do with this? It's quite simple at that point. what we have again, S1 and S2 and S0 here, right? So we're going to look at this triangle basically based on the point that it strikes the prism. So we know theta minus theta k, we found it to be a n minus 1. So then look, this portion is d over 2, this portion is a. Then if we have an approximation for tangent theta minus theta k, that would be d over 2 over a, right? So now for this, for sake of the approximation, then this left-hand side is almost theta minus theta k, which we found here to be a. So then let's put that there, a times n minus 1, d over 2a. From here, then the distance between the sources is going to be 2a, capital A, n minus 1, which is exactly what we were given in the beginning to prove. Now, in part B is much straightforward. So delta y is going to be equal to r times lambda over d. As you know, applied the approximation applied here. So now we know what d is, r lambda over 2a capital A n minus 1. Let me remind you one thing. R is the total distance from the source to the screen. So it's A plus B, actually. A is given to us as 0.2 meters. B is given to us as 2 meters. So that's the addition is what we're going to put in the equation. So it's going to be 2.2 times lambda is given as 500 nanometers. So convert that to meters divided by 2 times the A is 0.2 meters again. Capital A is given to us as 3.5 milliradians, so 10 to the power of negative 3 radians, right? And finally, we have n minus 1, n is 1.5 minus 1. So if we do the algebra, we're going to get 1.57 times 10 to the power of negative 3 meters, 1.57 millimeters as the separation distance between sources S1 and S2.